Okay, so it's a great pleasure to have Minh speak in our department seminar. All of you, I think, know Minh. He works with Gary. What you may not know about Minh, and what intrigues me a little bit, because I've not explored that aspect of Minh, is that he plays the piano. And I'd like to hear him play the piano one day. But anyhow, so over to Minh.
Yeah. So thank you. Good afternoon, everyone. Thank you for coming. So this talk is based on a joint paper written with Kerry. But also, I also want to thank a few of my other authors whose idea I have stolen or mischaracterized for this talk. So just a word of motivation. So here I have given you, on this left here is what is called as a graph generated from a data set on the visual motion detection circuit of a Drosophila fly. So this graph was obtained by, first of all, tracing the neurons. So each of these is supposed to be a neuron in the, what is called the visual cortex columns of the fly. And there's supposed to be 1,748 vertices, roughly 8,000 edges. 379 neurons are considered important neurons, which form a column in this cortex. And we then have edges connections between these neurons and some other neurons around the surrounding columns. So this was what the graph looks like when we connect edges. And maybe one of the aim is to hopefully partition the nodes of this graph into groups of clusters. In this case, what they care about is the columns of visual connections. So I run some algorithm. I get this clustering into 8 groups of clusters. And then if I rearrange the adjacency matrix on the right hand side there in order according to these blocks, then maybe I see some structure such as that it seems like all the blocks I get are densely connected within and maybe loosely connected between. So that's roughly the idea of what we meant by clustering of a text of a graph. And so the main algorithm I will concern in this talk is what we call spectral clustering, which refers to a class of inference methodology for partitioning the vertices of a graph by doing 2 steps. First, I do a spectral embedding, which means I take the graph, the adjacency matrix, I find a low-rank representation. So if the graph has n vertices, I hopefully to find a collection of n points in d-dimensional space for some d much less than n. The graph is originated n by n vertices, now convert it to n by d for some d much less than n. Now each of these vertex is now a point in Rd, so I could cluster points in Rd via some classical clustering algorithm. So 2 methods of finding low-rank representation are what is called as adjacency spectral embedding and normalized Laplacian spectral embedding. We will discuss this a little bit later. And but once we get a low-rank representation, we can proceed via either k-means, the classical procedure, or assuming that each clusters of points correspond to a Gaussian mixture. So we could do Gaussian mixture modeling. So the aim is that it is not clear which choice of combination of embedding methods and clustering procedure is preferable from one to another. So we hope to answer that in a bit.
So, Minh,
yes.
Just a quick question. So maybe you will talk about this later.
Yeah.
So when you said this spectral embedding is going to do a low rank embedding of the adjacency matrix.
Yes.
So you said that okay, for every vertex you're going to get a bunch of vectors in some low dimensional Euclidean space.
No, for every vertex I'll get a point in Rd.
Right. Right.
Yeah.
So and then right, a single point, and then so you have these endpoints in Rd.
Yes.
What's the connection between these endpoints and the original adjacency matrix?
The hope is that I will come to a model for which that operation is well defined and meaningful. So each vertex is a point in Rd, and I hopefully will be able to characterize that the points in Rd will induce the geometry of the graph back. So I hope to come with a model for which that reverse engineering procedure is meaningful. Thank you. Yep. So just to define terminologies. So I start with the graph A on n by n vertices, given an integer d less than or equal to n. any. I suppose I decompose the eigen-decomposition of A into this form. UA here is the n by d matrix. SA here is the d by d matrix of diagonal eigenvalues containing the d largest eigenvalues of A, or d largest eigenvalues of the absolute value of A. And then UA is the matrix whose columns are the corresponding eigenvectors. So my HCC spectral embedding here is just basically taking the truncated representation of A. So what of absolute value of A? What that meant is that I would just take the eigenvectors in UA, multiply with the eigenvalues in SA to 1/2. So like I said, n by n matrix will become n points in RD, the embedding matrix. The Laplacian spectral embedding, which is also widely used in the literature, is also defined roughly similarly. So instead of taking the eigen-decomposition of A itself, I first of all obtain this D, which is the diagonal matrix, whose entries are the row sums of A. So just like the degree of the vertex in the graph. Let script LA be this matrix D minus 1/2, A D minus 1/2, which is called the normalized Laplacian. And once again, I take the eigen-decomposition of this script LA matrix, take the D largest eigenvalue and the corresponding eigenvectors, and form this matrix X bref, which is U tilde A, X tilde A 1/2. So this here, two embedding procedures starts from a graph. I could get two different representations of the points. So the question becomes, which representation is more amenable to subsequent analysis? But before being able to do that, I have to be able to say clustering is a weird problem. Because what does it mean to get a cluster? So usually the question that is answered in the literature is to assume a model, a generative model on the graph for which clusters is available. Yes?
Can I ask a question on the preceding page?
Yes.
So in the first spectral embedding you talked about,
yes,
it was clear that the matrix that you were, for which you were giving a spectral decomposition was positive semi-definite.
Yes.
Here, L of A might have negative eigenvalues.
Yes, that's why I put the absolute value here.
Oh,
which,
okay.
I defined the absolute value earlier in this case.
Oh, okay, yes, thank you.
So,
thanks.
Yeah. Yeah. So, like I said, one of the things that we want to do is first to come with a model for which there exists underlying community structure. So the most universally used and simplest model of such a form is what is called the stochastic block models from the classic work of Holland. So this model, roughly speaking, just says that you have a graph of n vertices. For each vertex, I will assign it to a community at random. So I have a vector pi here, which is a property vector. And then I have a B matrix here, which is the matrix of H probabilities. So to generate a graph of n vertices, I follow the procedure that first, I sample for each vertex its community membership. So that's categorical pi. So the property that the ith vertex is in the kth community is pi k. And each vertex only have a single community. Then to form the edges, I just flip coins independently at random, where the property of having an edge between vertex and vertex j is just a function of the community membership of vertex I and vertex j. So in a sense, there are k blocks, there will be k communities, and each vertex gets mapped to one of k different communities, but the edge connection is defined by the community structure. So in a sense, this is the simplest model that, like I said, have underlying community structure. So we will use this model to answer the question, which choice of embedding methods and which choice of clustering procedure is to be preferred. So a paper that motivates this work was a paper by Punamrita Sarkar and Peter Bickel, who showed for the very specific case of two blocks stochastic block models that for a large regime of parameters, the normalized Laplacian spectral embedding reduces the block variance, the Witten block variance of the embedded points, while preserving the Witten block variance when you compare this to that of HCC spectral embedding. So if you reduce the Witten block variance, while preserving the Witten block variance, this suggests that for a large region of the parameter space, the Laplacian spectral embedding is to be preferred over the ASE. Except, while this is a nice result, there's a difficulty because the metric in Sarkar and Bickel is, however, intrinsically tied to the use of k-means. as clustering position. And what k-means of some property, we know that it may not be always optimal unless the clusters are spherically Gaussian, which turns out to be not the case. So the outline of this talk is that we will address the following results. So Avanti area and some of us provides a central limit theorem showing that the top D eigenvectors of the adjacency matrix for SBM has distribution that approaches the limit as a mixture of multivariate Gaussian. So each vertex, if you do the embedding, it looks multivariate normal around the true latent position, whatever that meant. We will talk about that in a bit. So Kelly and I provides an analogous result for the eigenvectors of the normalized Laplacian. In both cases, we showed that the distribution of the embedded points is not spherically Gaussian, so k-means is inferior to Gaussian distribution modeling for spectral clustering. We then propose a metric for spectral embedding of ASE and LSE in the context of clustering that is independent of any specific clustering position. So what we meant is that no matter what clustering you do after you embed the graph, without going back to visit the graph, no matter which clustering procedure you use, your performance cannot be better than this. We have a lower bound, and so it turns out that, not only do we have a lower bound, we have in a sense, the exact optimal rate, and so we can show that the choice between these embedding methods turns out to be a sticky wicket because neither methods dominates the other for subsequent inference.
So, sorry,
yes.
Does this mean that the minimum error is achieved by some specific clustering procedure?
Yes,
okay.
It is achieved by some clustering procedure. In fact, it is achieved by Gaussian modeling. Yep. So, excuse me?
It would be asymptotically?
Asymptotically, yes. Yep. So I talked about stochastic block model graphs, but it turns out that it's easier to present the result in the framework of random block product graphs because stochastic block model graph, you only have community membership, so it's not clear what the points represent. But it turns out that the random block product graph is a reasonable generalization that gives you stochastic block model graph back. So Ed Schneiderman and one of his PhD students consider this model for which omega is a subset of d-dimensional Euclidean space, holds inner product for any 2 points in omega as between 0 and 1. And now if I let add the distribution, taking values in omega, I could define a random graph model as follows. I sample endpoints IAD according to the distribution F. And let this both X be the n by P matrix of the latent position. And let P be the matrix XX transpose, so the property of connection between I and J, or the Pij here is the matrix of H property, which is the inner product between Xi and Xj, between 0 and 1. So to get the graph for any 2 vertex, I flip a coin. The property of success is given the inner product between Xi and Xj. And so that gives me a H-independent graph conditioned on the latent position X. So I would write AX as RDPGF, just to refer to this generative procedure. But I want to emphasize that we never observe this X. We only observe the graph. So usually that's why we usually write A RDPGF also, to refer to the fact that we never observe the latent position, so we have to estimate it, which is our aim. Okay? So the main thing, like I said earlier, is that if F is a mixture of point masses, then RDPGF is a stochastic block model. And there is a slight converse that say that if any stochastic block model can be modeled as what is called as a generalized RDPG. So, which we also have results for, but for simplicity, we'll represent the RDPG here. So the idea is that the random block graph is a very specific example of one of the most popular random graph model, which is called latent position graphs. It's popular because it's the kind of the only thing that one could do analysis on because of the independent edge property. So the latent position graph just assumes that each vertex has a latent position, and then the edges are conditionally independent, where the property of edge between 2 vertices is given by the function of the latent position. So in a sense, the function could be very arbitrary, but if the function has some nice properties such as continuousness, then any latent position graphs can be approximated by stochastic block product graphs if you have inner blocks, or by random block product graphs if you have enough embedding dimension. Because if you can think of the latent of this latent link function here as the kernel, then the kernel can be approximated arbitrarily well by lower dimensional embedding. One thing I want to emphasize before we move on is that the random doublet graph is not unique. What we meant is that for any choice of distribution f, if you rotate the latent position by orthogonal transformation, you get back the same inner product. So in a sense, you cannot recover the latent position, you cannot recover the distribution up to uniqueness. You can only recover it up to some orthogonal transformation. But for the purpose of clustering, that's not the issue, because one-to-one invertible transformation doesn't change the resulting clustering performance. Okay? So our main aim is to show that the spectral embedding of random doublet graphs yield us meaningful result. So it turns out that that is easily observed from this very artificial example. Let's suppose here I generate here as 1,000 points in two-dimensional space. The blue points are sampled according to some Dirichlet, and the red points are sampled according to some other Dirichlet. Okay? So if I form the matrix X transpose here, which is the matrix of H probability, it looks block diagonal form. So densely connected here, and maybe less densely connected with here. So now if for each of, if I generate a graph by substituting for each edge, the property of connection being Pij, then I get this random sample from this matrix, which is my adjacency matrix here. And the main thing I want to just emphasize is that if we squint, this matrix looks roughly like this. Even though this matrix is just 0, 1 entries, and this matrix is continuous entries. But on the rough look, large scale, they look similar. And it turns out you could make this more precise. So it turns out that the spectral norm difference between the two matrices, the graph and the H matrix, the matrix of H property P, it turns out that you can show that their spectral norm difference is bounded by, say, the square root of the maximum row sums. Now that may not seem like a lot, so let's suppose consider a dense graph where this maximum row sum is maybe of order n, where you have n vertices. Then this spectral norm difference of the square root n. But it turns out that each of the graph by itself has spectral norm of order n, because there are n entries and they are either 0 or 1 or something in between. So the spectral norm difference is of the square root n, but the spectral norm for each of them is of order n. So classical result in perturbation analysis says that indicates that these matrices are close in some norm. In this case, the spectral norm. And so you can show by some classical perturbation results in the Davis-Kahan theory that says that if you look at the spectral embedding of x hat, which is spectral embedding of our original matrix A, that should be in the Frobenius norm close to the matrix X, which is our original latent position. So let's go back here. So the main thing that I want to emphasize that if I observe P, then from P I can take the eigendecomposition and I should recover back X up to orthogonal transformation. So if A is close to P, the eigendecomposition of A truncated properly should give me that for X. So we can show that the Frobenius norm difference is of constant order. OP here just means the bounds hold with high probability. So this doesn't seem to be that great, but it turns out that because each of the matrix X has n rows. So the Frobenius norm is of constant order. On average, each row is of order 1 over square root n. And that is enough to say that you can get good clustering performance. But this is not enough. This is only an upper bound, so this is not enough to get a real tight characterization of subsequent clustering performance. So it turns out that using a more refined approach based on power method observation, we could get a better refined error bounds. We'll discuss that in a bit. So the same phenomenon holds for the Laplacian spectral embedding. So the Laplacian spectral embedding here looks like this matrix here, t minus 1/2, p t minus 1/2. So the Laplacian matrix of the adjacency matrix looks like the Laplacian matrix of the H property matrix, in the sense that now the spectral norm difference is going to 0. Here is gamma p here is the minimum average degree. Once again, for dense graph, the minimum average degree is of order square root n. So this spectral norm difference is of order 1 over square root n. But the spectral norm for each of these matrices is of constant order. So once again, because of the normalization here. So once again, perturbation analysis tells me that the Frobenius norm is bounded above by 1 over square root n. So we see that it's not that easy to compare these two methods because they are giving you different representation of a graph. In one case, I am representing my local position x. In the other case, I'm representing a transform version of my latent position x. So that's why I cannot just compare them based on simple notions of like within. I have to do something a little bit more elaborate. But once again, this is an upper bound, and so I could do power method to get a more refined improved bound. So that is what we have this result here. So we will first present the result on law of large number for the GC spectral embedding. So if I have a sequence of the dot product graph for every on n vertices, for n from 1, 2 up to so on, if I let Pn be the matrix of H property for the n graph, then for any member in the sequence, there exists an orthogonal matrix Wn such that the difference here between the latent position for the x hat, the estimated latent position, and the true latent position of the orthogonal transformation can be written in this form here, where the residual term is of smaller order than the original term. The reason why I want to write it this way is because the right-hand side here is just a function. If I condition the xn, this is just a linear function of the independent random variables an. So once I condition xn, I have pn. So an is random Bernoulli with pn. So this here is just a linear quantities in terms of an and spn. And that's independent, some independent random variables I can easily analyze. So using some concentrational inequalities result, I can show that the Frobenius norm differences of this residual will converge almost surely to this matrix that is given just from the distribution f itself of the underlying latent position. So previously, I have an upper bound bounded above by a constant, but now I can say that it converges almost surely to some constant as the number of vertices n goes to infinity. So this is one part of the argument. But more interestingly to me, though, is the fact that if I can write it of this form, if I ignore the residual term, then if I let x hat n I be the ith row of my HCC spectral embedding, then this difference is the ith row can be written in terms of this linear combination of the independent entries a and ij minus p and ij summing over j. So for any I, the ith row can be written as a linear combination of the independent entries a and ij minus p and ij, because I'm summing over the j only, plus the residual term, which turns out will vanish. So this is now a sum of independent random variables suitably scaled. This part will converge to a constant. In fact, it converges to the matrix delta here we defined earlier. And so this is a fixed sum of independent mean zero random variables. So I will get a central limit theorem for my HCC spectral embedding, which says that once again I have a sequence of graphs. If I let the ith row be x hat in, x hat ni, then there exists a sequence of orthogonal transformation such that the probability density function converges to a mixture of multivariate normal. I have to do a mixture because the x and I are not could be on a set of measure 0, so I can really condition properly.
So it's scale mixture, or covariance matrix mixture?
Covariance matrix mixture.
Yes. No mixing in the location.
No mixing in the location, yes, just mixing in the covariance, yes. Yeah. So the covariance matrix is a little bit messy, but it is what it is, and we don't really care too much about it, except that we can plug it into the computer to get something else later on, more meaningful. So the sequence converges in the distribution, the mixture of multivariate normals, This is for random dot product graph. So for my stochastic block model graph, because I am now a mixture of point masses, I cannot condition on the point masses. So in the case of stochastic block model graph, where the random dot product graph distribution can be thought of as a mixture of point masses with mixture location, nu k here, then I can condition on the fact that the ith vertex is assigned to the kth point masses, and instead of getting a mixture of multivariate normals, I will just get back a multivariate normal by properly conditioning. Okay, so this is the case for the HTC spectral embedding. I will have a similar result for the Laplacian spectral embedding, except now it's much more, not much, but somewhat more messy. So once again, I have a sequence of random dot product graph. Then if I look at the Laplacian spectral embedding, let's call XREF n here, and then there exists for any fixed n or orthogonal matrix W tilde n, so the difference between my Laplacian spectral embedding and the transformed latent position. So I multiply this on the left, which means that I scale each row differently. That the differences here can be once again written as, on the right here, a linear combination plus the residual term. And once again, I want to emphasize that if I condition on xn, then Tn is given. It's just the expected degree of the P matrix. P is also given. So once again, I have here a linear combination of the independent entries, An minus Pn, and a linear combination of the independent entries, Tn minus Dn. So once again, it is a sum of independent random variables. So I could apply another concentration inequality to show that this difference now scaled by n because of this Tn minus 1/2 factor here. That this difference in Frobenius norm once again converges to a constant, and you could evaluate this constant, and it's a little bit messy, but it is what it is. Here the expectation here is taken with respect to C1 and C2 being supposed to be IAD with distribution F. So it's taken expectation with respect to two random variables, just because there is the inner product between C1 transpose C2, which makes things a little bit more messy.
I have a question.
Yes.
Can you analyze this constant at all? I mean, in the sense that can you show that the constant is uniformly bounded in the choice of the model or something? You know what I mean? In the choice of F?
I think you can, just because if you assume that the H property is never 0, then because H property is always bounded above the 1, you can show that it's bounded above and below by some. I don't know what constant it is, but the choice that you can show that. But once again, this law of large number is of interest, but more interesting to me is a central limit theorem for this expression here, and that is once again easy, because if I now let the x prime and I, the idea of x prime n, then from this decomposition here, I can obtain the expression for the ith row, and so you have here this matrix and transpose this one here that becomes here, this one then becomes this matrix, then becomes a scaled sum, and this matrix then becomes this scaled sum, which is once again a sum of independent mean zero random variables. And so after some further manipulations, I can show that a central limit theorem similarly for the Laplacian spectral embedding. So in this case, I scale by n because they have different quantities, and it turns out that it is once again a mixture of multivariate normal with now the covariance matrix becoming much more messy. So this is in the case of random dot product graph. I can once again condition on stochastic block model to get a spectral, to get a central limit theorem for the latent position in the spectral, in the stochastic block model case. So most of these expressions here look messy. So in a very specific case, where under a very simple model, where I just have a two-block model, but the latent positions can be thought of as rank 1. So B here is P squared PQ, PQ, Q squared. So this is a 2 by 2 block model, but the rank of this matrix B is only of rank 1. this corresponds to a random number graph in one dimension, where the related position is either P with property alpha or Q with property 1 minus alpha. Then my AAC embedding tells me that each of the xi is centered around P if the xi is really equal to P, according to this normal distribution, and centered around Q according to this normal distribution and equal to Q. I want to emphasize here that it's obvious that these two covariance matrices are not the same. Okay? This covariance matrix is different from this covariance matrix. And that's the same phenomenon also Laplacian spectral embedding. Here I normalize by different vector, and once again the two covariance matrices are not the same. So if the covariance matrix is not the same, or in this case the variance is not the same, then one can easily show that Gaussian mixture modeling is preferable to k-means, because k-means assumes vertically symmetric. So this is that figure in a simulation. I have here the performance as the number of vertices in the graph increases. The green line here is what happened when I embed using Laplacian spectral embedding and then k-means as n increases. This is the misclustering error, and this is k-means, and this is Gaussian mixture modeling. And I can see that Gaussian mixture modeling has, in a sense, a much smaller error rate by maybe a factor. And not only more, I can also see that if you compare it with if I generate the points from the distribution and do the best I could do by a linear classifier or by Gaussian mixture modeling, then I can see that the performance I get from the generating the graph of generating the data according to the distribution are roughly comparable. So it means that my theoretical distribution, my limiting distribution is, my last sample approximation is doing well at around 4,000 vertices. So now I want to say, okay, so Gaussian mixture modeling is preferable to k-means in both cases. But I have not addressed the question of what choice of embedding method, which is spectral embedding or Laplacian spectral embedding, is to be preferred. And to do that, I will introduce this notion of chain-off information by chain-off 1952. So roughly speaking, if I have two distributions f0, f1 on RD, with density function little f0, little f1, and suppose I have m points ID some distribution f, with either f0 or f1, and I want to test whether from these m points my distribution is 0 or 1. Then the Lemma and Pearson lemma states that the likelihood ratio test is most powerful at circumference level alpha m. So if I assume that I have the prior property that the null hypothesis h0 is true, or that the property that the hypothesis f equal to f0 is true, then for any fixed type 1 error, if I let beta m alpha m be the type 2 error of the likelihood ratio test, then if I take the infimum over all type 1 error, I get what is called the weighted risk in deciding between these two hypotheses, f0 or f1.
Wait, are you telling me that you and Carrie are now doing a Bayesian model of hypothesis testing?